It's not very. I guess you have it because we have I mean, this sounds like something that somebody, maybe Edward Kmet, may have implemented.
Yeah,
so
I think Kmet's done this.
yeah. So that's
It's in contravariance.
okay.
Yes, it would be because it's definitely. So what you could do here is you could implement it for divide, and then you would get it for all type classes that have a divide.
What do you and then how?
An equality can have a divide. In fact, equality can have a divisible.
Yeah, but I don't see what. So the divisible would be like some kind of functor, isn't it? And then you mean instead of this, like implement for every divisible functor? Maybe you can. You can always go up into the ladder of abstraction. This is how you usually do things here.
Every single implementation of a contravariant type class like this is going to look exactly the same.
Yeah, actually, I don't think you need this because this is actually like, yes, all these functors are representable functors. So you could get like, the representable functor gives you a representation in another sense. So you can get the repr of the rep of these things, and I think you can do this way. But let's keep it like let's keep it like not so weird. Like yeah. Let's just try to write the last case here.
How come your info is so small?
Huh? So
my info on the bus case is gigantic.
Huh?
Info.
Oh yeah, the info, because that's every information it knows for plus, so it knows that it's an Oh yeah, because that's the representation for the functor of the representation. So that's a very weird thing. But no. I have it down here. Don't worry. Here it comes.
Okay.
So no.
We are looking only at the top.
Yeah, we are looking only at the top. So that's what that would be the thing. You may also look at the documentation, which will only have like the first line. But opening Firefox now would take us 5 more minutes. So
What's a metacons?
a metacons is just so it's a way to put several metadata together. So sometimes you want more than one piece of data over something. So you have like a cons of 2 metadatas.
Okay.
So let's.
The first case doesn't have the operator constructor.
Yeah. So
okay.
we can both go on the left, and then okay, let's just keep looking if they are equal. We can also go on the right in both cases. And then what we could do, well, in just the rest of the cases, they are false. I mean, so we have generic equality right now for our. That's everything we had to implement. So these are all the cases we need. Hopefully it will all compile fine. Yeah. So the last step, as I said, is you don't really want to like call to and from together. So you always end up defining. Well, this will be we are using EQ, so EQ will be just. You won't do this for EQ, but let's just define equality for A, and then for T, and then we have like the, I don't know, equal equals just to not collide, which tells you T to T tuple. Okay, and let me replace this with equality, so everything is things we have defined ourselves. Yeah. So these are all things we have defined ourselves. So what you would need to do now is to write yourself. That's not an instance, that's a class. So the instance for equality of a pet can be just written as so P1 equals P2 if you use the generic operation on to P1 and to P2, and hopefully this will be the one. Otherwise, it's from. Yeah, it's from.
I can also never remember that.
Yeah, that's.
I also do it with to-and-from exception.
What's going on? And we have, yeah, and this is something I forgot because we are using real generics. quality f, we need to define yet another case, which is the metadata one, the metadata thing. So that's metadata m over f, where, and then I think this is how it has to be. I always forget about these things. Well, it tells me now. Oh, and now we don't have equality for charge because we are okay. Let's define a couple more. So we need to define our generic equality over strings over.
You can define equality based on eq.
Yeah, I'm gonna just do like this for every other thing, and hopefully this will work. And it tells me there is no equality for color. That's good because we control color, so we can do equality for color, where a color 1 equals a color 2 if equals from C1 from C2. So
Back up, what's the reason we have to have equality for this?
sorry, just 1 minute. What's? Yeah, so I'm just trying to like define. So in order to do this, remember we said that we need to define equality here. So we said that if we want to define generic equality for our field, this field has to have an equality associated with it, which is like the normal thing, not the thing which operates on representations. And that means in this case we need to have like an equality for int and for a string and for all of this. That's because this is kind of a weird example because you will just use EQ. But imagine that there is no EQ and we are defining all of it ourselves. Then we will need to define really like all the things. So I'm just sort of, because I want to explain you a bit about the rest. I'm just piggybacking on saying, okay, for some data types like list of int, list of things, I can. That's good. So yeah, this is a hack. Just look here. The important part is here, which if you want to define equality for something you control, for a type class you control, you just turn it into the generic representation and then apply the generic function. So that's the magic, where the magic happens. And as I say, well, I cannot copy this here because actually int needs to have like a primitive equality from the compiler in this case, but and for show. But for many other things, you just do like your own things, and then you just always use your equality. What I really want to emphasize that you always end up with two type classes which are recursive. So you always end up with like equality, which operates on data types, and it only does one thing, which is turn your things into the generic representation and call the generic operation. And then you have the generic equality, which operates on representations, and usually on the field case, in the K1, calls back equality. So it's like a kind of this idea of I turn a bit into the generic representation, I try to do a bit of generic equality. If I need to look farther, then I go back to equality. So I look a bit more, I turn a bit more into generic representation and go back. So this is all very like with the Haskell laziness idea. So that's why it's like also set up.
So one curiosity. Imagine that we had another data type called bad cat.
Yeah.
With bad dog, bad cat, and bad fish as constructors. They are structurally the same, just the
you could call
constructors would be
you could call from, and then turn it into generic representation, and then call to and go back to the other bad pet. Yeah, that's possible. I mean,
yeah, but that's not where I'm going. Right now, our thing would not type check.
Yeah, the equality won't, but you can define this operation. So there are some checks in different parts. So this equality above just checks that they have the same structure, and it's only here in equality where you really check that the two t's must be the same.
Imagine how would you make an equality where it checks for the structure, not
Oh, yeah, you can just change. Okay, you change here. That works for every A and B such that the representation of A equals the representation of B. That's possible. And now you can define it. So this is, but again, we have a boring thing. This is the same thing. So let's introduce the final thing that GHC does, which is called default class definitions. So in general, you know that, well, you have, imagine we have non-equals, and you know that you can say, well, x is not equal to y if not x equals y. So this is called a default definition. If you don't provide a definition here, it's sort of just copied from there down here. But GHC introduces a slightly refinement of this, which is sometimes you want to use a default definition, but not always. So in this case, you want to use the default definition only if there is a generic instance of the data type. So you can, let me show you, and maybe it will become clear. So I can say, I will have a default definition for equal, which only works if I have a generic, so if sorry, this should be t. Only works if t is generic, and then this is just the same thing. And then this equals is just, you know, it's always the same thing. It's just copying this. And so I can remove this. And it will tell me that I have to add some extension, which I don't know, default signatures, good. Language default signatures. And then yeah. And I don't only need this, I also need to have a generic equality for the representation of t. And I need more. Sorry, this is just fixing the thing. So just, it asked me about flexible context. Let's make it happy. Yes. So everything what we are saying here is, okay, if it happens to be the, and again, this is a pattern that happens very often. So if our t is generic, and actually we are able to have generic equality for its representation, because, you know, you may have forgotten to define what is the generic equality for the sum. So then you cannot handle things which have more than one constructors, and this might be a good thing for you. I mean, there are some kind of there are some kinds of generic operations that might not be defined for some types. Like I could imagine, like, if you have a JSON encoder, maybe you say, oh, I don't want to deal with some types because this makes my JSON very ugly. So I will just define it for products, fields, and no fields. That's a possibility. So now, if I have the quality of pet, I am getting the non-equals from the default definition and the equals from this default definition because it's generic, because I derive generic, and the generic equality works for this. So in practice, how you use GHC generics is by having these two type classes, equality and G-equality, calling each other. And then in equality, in the real one, you define a default operation, which just makes the from and calls the generic one. And then, well, you need to write instance there. But if you add yet another thing, you can even say, I think I need derive any class. But let's tell. Oh, yeah, that's, yeah. So I need derive any class. So suddenly your thing has become like a built-in into GHC. So now you can derive equality, and this is how, for example, ASON does to JSON and from JSON. You just put the derive there, or you write the instance empty, or you derive any class and then put to JSON. It's how binary does things. So that's how it works. That's all the bits and pieces. So if you didn't have enough, I can tell you about SOP, but maybe we can also like have questions and break for 5 minutes and then in 15 minutes I can tell you what are the difference with if you do.
Scroll down a little bit.
Sure, sure.
I want to see the default.
The default is just what we were copying several times. So we just turn our thing with from into generic representation, and then we call the generic equality. And so if you want to do metadata, what you need to do actually is to handle this case, this M1 case, which I handled this by just saying I don't care about you, caring about it. So you look at the M, and then the M has information about what you have, and then you hold the case accordingly. So it's...
For example, a crowd wants to extract the name of the constructor.
Yes.
And the name of the constructor is present in type level, but not in runtime.
Yes, but you can do this here, like, so...
That was a puzzle I didn't solve.
Yeah, but it's only at type level, because, I mean, at runtime level, there is no information about that anymore, even in the runtime. So, but if you want to define like generic show, you don't need to know at runtime which was the tag. You only need at the compile time, extract it and put it there as a string.
Sure.
So,
I was not able to do that.
oh, if you try later, I mean, you can try and solve it, and we can. Otherwise, I can help you. Yeah. So you can try to define. So something which is quite useful is now try to define OR and just have an order saying, well, if I go to the left, that's smaller than going to the right, instead of, but just using the same framework for all of this. That's something you can do. And if you want to go a bit more crazy, say, okay, I order my constructors by name. So now you have to go to the metadata and check. You will get the two strings about what are the names, and then you check that which name is smaller. That's something you can do as an exercise for this. I really want to also emphasize that there is not much code. So we have the generic equality is simple, but that's all we had to write. So which is not that much, given the fact that everybody wants to define their generic. I mean, yeah. Just depending on what you might need to want to look at the name of the fields and things like that. But yeah, it's pretty much the same.
What's the name? So U1 and K1 and L1 and those, they're all.
Yeah.
Are they all part of the?
Yeah, it's in GHC generics. So GHC.generics, that's
structure that represents the generic
yeah.
information, right?
The constructors.
Yeah. So that's what I call.
Like the different parts of it, like the product and the.
Yeah. So this is what I call both the star, and then L1 and R1 are the one on the left and the one on the right.
And what's?
I'm still.
What's U1 and K1 and L1?
U1 stands for unit, because I said like the no field is like a unit tuple, so that's like
okay,
unit.
It's just if it's a no
fields.
Argument
No,
constructor.
yeah, exactly.
Do we compare the tags though or not?
Well, here we are comparing, but they are always equal. I could also say equals is const true. I'm just doing this because I wanted to pattern match everywhere.
But U1 does that?
Yeah, because it's the same thing. Like an empty tuple has a constructor, which is like the empty tuple thingy. So you can just pattern match on this.
But if we had two empty constructors, like
yeah, but we will hold it because one will go through the OR, and then this will recursively call equality on the first U1 or in the second U1. So you can have two U1s. That's not a problem. That means you have two constructor which has no fields, like a Boolean, true or false.
Where will they be disambiguous? Like where will they be not comparing to true?
Because of one, because that's U1 plus U1. So one will be L1 of U1, and the other one will be right one or U1. So you go to the left or to the right, and then there is nothing.
That makes sense.
So there was a question at the back.
Oh yeah, I'm curious why it's defined as separate types, like the generics type, and why it wouldn't be defined as like a single type. Because if you have a single type, then you'd be able to like have a fold or like a metamorphism that uses a single generic type.
You mean all these things? Yeah. So let's go to generics SOP, because that's actually the right thing to do. So the reason why you didn't do this is because you could not, by the way this one defined, you didn't have enough of Haskell nuts, bells and whistles to do this. Yeah, but you can do that. So generics. Huh? Oh yeah. Let's have a break, and then I just got excited. Sorry.
You asked the right question.
Huh?
Can we do the labels after the break as well? Like an encoder that needs to maybe.
Yeah. Let's.
Are we in the break? No?
Yeah, we are in the break now. I'm just so I will spend the next five minutes writing language pragmas, so we don't have to write it later, okay? And then I guess when you're back, I will be done, hopefully. So, okay, so let's try to do the other kind of generics. This will be a bit faster, I guess, because I don't want to, well, I mean, I can keep talking as much as you want, but at 12 I want to eat, so that's the only thing. So let's move, like 10 years time. We are now, it's 2018, hopefully. And we have many more things in Haskell. In particular, we have something very interesting, which is this data type promotion. The fact that we can have a data type and use it as part of a type. So it's like dependent, it's like, well, fake dependent types in some way. So you don't really need to understand all data type promotion. The only thing you need to know for this is that you can have type level lists. That's the only thing that we will use here. Like this. So what if now our representation of a pet is actually a sum of products? But because having our own constructor is just boring, let's just say this is like a list of lists. So the outermost lists give us a choice of constructors, and then each constructor is just a list of its fields. You know it. I mean, as simple as that. So this is how we want to represent pet. So this is what we want to do. So, we will actually be able to do this. But this is what we want to do. We want to say that pet is this. No more plus, L1s, or ORs, and weird things. And because now it is this way, you cannot really make it wrong. You cannot have somebody asked me before, like, what if you have a plus inside a product instead of the other way around? Well, you can do that in GHC generics, but not in this generics SOP.
Okay, I'm sorry. This reminds me a lot of like terrible Java code and like two-string methods.
Oh, this is type level list. So it's a type level at compile time.
Okay, so I mean the quotation marks like.
Oh yeah, sorry about that.
What do single quotes mean?
The quotation. Oh yeah. So this is a type level list, and I have to say this is a type level list by having a quotation mark. So this is just when you want to bring something like from the term level up one level to the level of types, you have to quote it like this way. So now there is.
Do you do the single quote over here on the keyboard or the single quote over here on the keyboard?
Not the backwards quote, the single one. Yeah.
It's one of the language extensions that brings that in, right?
Yeah, data kinds. So that's the first one.
Data kinds brings the type level list, right?
Yeah, yeah, that's one of the things it brings.
Just basic, because data kinds is a compiler extension, and the compiler extension hard codes the syntax of prime square bracket open blah 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 square bracket close.
Oh yeah, it does. Yeah. So you can also use like yeah, you also have like quote column, which is like the cons, and this is not hard coded. This is just, but yeah, just to make it simple. So yeah, the quotes. So now you can have a type like this, which is just the type true one level up. So that's like the true going one level up. That's about promoted types. I don't want to go there. It's very useful, but we just need to know that there are type level lists. And in Haskell, they happen to be this way, but in other languages, they just have this built in or do it in any other ways you have. So the problem of this is, okay, what is the kind? So we would like to do wrapper of this, okay? We want to make have a type class like before, but we cannot do this. And the problem is in the kind of this thing. So, well, if you haven't looked at promoted data types, but in the same way that your types, your term level things become types, your types now go one level up and become kinds. So this is a list of types. So this is the kind of this representation. So it's a list of types. This is what this is saying, because types in Haskell is star. So this is the kind of the representation. And now we have a problem, because we cannot turn a t into the representation of t, because anything which you return or build in Haskell has to have kind of star. So we need somehow to turn this thing, this nice description, into something of type star. And that's the trick which we need to play this. So at the end, it's going to look very, very similar to the other thing. So we will have just a bunch of constructors like this. So let's try to do this. So I don't have much time to do this. So I will try to write the code and guide you through it. And if you have any question about what we are doing, please let me know. Also, like a terminological thing, because this thing is not a value. We don't call it a representation. We call it a code. So this is actually a code of pet. And what we want to do is to turn the code of pet, which is this list, into a representation of pet, which is something which exists at runtime. So we always have this interplay in this SOP thing. Again, not all of this is written in a library, so you don't need to like. But now, so in order to do this, you actually need to like bring in some GADTs and some extensions. But what we are going to do is to say, okay, what is the representation of one of these lists? So I get my data type, which is, as I said, a list of types. And I want to turn it into something which is of kind star. So I will use a GADT to do this. And this looks very fancy, but it's exactly the same thing as before. So remember, you have a list of things. So what you can do is, okay, you either take the first one. So that's what I call. I'm already here in my list. So it's the first one. I'm already here. I want to take the first constructor.
Data or class?
That data. Now it's data. I'm sure. Huh? Yeah, because that's GADT. Yeah, yeah. That's like the advanced part. I'm sorry. I'm happy to answer questions later, but this essentially tells you, okay, this is the representation of a code. So I want this to be the representation of a code, and I want to take the first constructor. And there might be more constructors later on, but I'm taking the first one. So this is, so I will keep it outside, but essentially it's like we have chosen C. And then we are going to have here the fields of C. So that's like, the only thing I'm doing is traverse the list and say, I'm here, that's because I'm taking the first constructor. Otherwise, I want to go there. That's like usual notation. People like this. And then, okay. Again, that's what I start with, a representation, but I don't want to go into the C. I don't want to go into the first one. I want to keep looking. So I just use the representation of the next thing. So if I want to go into the color string, I will just go there. So now I'm here. I'm in the second part, then there again, and now here. So now I'm in the third place. That's like a way to encode how many steps you do. It's the same thing as the L1 and R1. You need to say one more, I'm done, I'm here. And now we need to do the same thing for the fields. So now the fields, we're going to take a constructor, which is a list of types. And remember, then I want to have one value for each list of types. So here we had a choice, and now we want everything. So I will, either I'm done, and this are the fields I need for an empty list, so I'm done. I have no more things to do, or just we had no fields. So maybe I will let me call it done. I'm done, or I have something more. So that means I have a T and the fields for the next T's, and with this I get. So this is telling me if I want to build something of this type, something which encodes fields, with the first one is a T and the rest are TS, then I need a T. That's something I need. And now we are good because this is of kind star, because this is a list of a star. This is actually of kind star. So this is something we can ask to have a value at runtime. So we have the T. And then we go and have the fields. So this is the same idea as before. For the first list, we offer a choice. And we do this with here and there. And for the fields, we need to have one per each thing. So hopefully this will compile.
Space between the dash and the...
Oh, right. Good, it compiled. So now this trick was that, okay, I want you to give me a code, and this code is gonna be a list of things. But when I want to turn it into a value, I have to like apply these two layers. So I need to. So at the end of the day, the code for from and to will look exactly the same as before, because you are doing the same thing. You are saying how many constructors you have to move through until you get to the one you want, and then you have to give me values for every single field. The only difference here is by playing this trick of separating what is the data type, how it's represented at runtime, we were able to have this fancier description, this fancier code. So this is the idea in generics SOP. You just, instead of writing things this way, instead of using the generics, you just define a list of types which define your data type.
Summarize it. The goal of this is to basically create a single uniform definition of how the...
Yes, so we really want to have like a choice of constructor, each of one being a list of fields. So because we want to enforce this, we do this. And the nice thing about this, and what it makes really nice to work with, is before we had to define our terrible G equality because we had to pattern match on types. But now we have a way at runtime, a way to pattern match on things. So we can pattern match on these things. So now if we want to do generic equality, so which works on some representation, and give me a bool, I just write it directly. So I just go and say, okay, I have a representation. If I'm here, then I will go into the fields. So I will have a there y, that's going to be xy, and GQ of any other thing is going to be false, where GQ now works on list of fields. So, and I just do, either I'm done and I'm done, or let me just. It's going to be like E x equals x prime and y and GQ prime x y prime. So this is how this won't compile.
Line 30 has it down on the...
Where?
On line 35 has it down on the results. Should be a bool.
Where? A bool, yeah. So it should be true.
Line 31. I believe this.
Yeah, that should be GQ prime. Yeah. So well, this is as nice as you can get. You are really saying in the most efficient way, if you have the same constructor, then go to check the fields, and if not, they are. I mean, if you have to go farther, then go with there, and otherwise they are false. And what it's even better, because this T reflects the shape of the type, I don't have to check the other case. It's impossible that I have a done and a thing with and. Because these T have to coincide. Whatever constructor they are, they must be fields from the same constructor. Otherwise, there is no reason to call this thing. It doesn't make sense. So
does this have a better performance?
So in principle, yes, in the sense that this doesn't have to have dictionaries, but there is a lot of work being put in doing GHC generics fast. So actually, GHC when you write your own generic thing, there is an extra pass which like removes all the things, and it's like handwritten thing. So you cannot beat that. It's
So the line with the theirs, is that GEQ prime?
where?
The line with the theirs.
Yeah, that's GEQ, because remember that when I have a representation, if I'm there, that means I have to go one step and they have a representation. That really the types inform you a lot what's here.
All right, I know, I see that.
Yeah.
So, and what's a colon star mean?
A colon and star is just a way to say and. So it's like you have a list of fields, but instead of calling it, because you cannot really have like, well, I'm just calling it colon and star, so it doesn't clash with the colon and star colon. Huh? It's a cons operator, yeah.
The cons and products.
Yeah. If you have done it, you might have. No, this is like the fields is like an H list. So it is actually like the definition of an H list. It's an list which has different types on every different thing. But we call it. I'm calling it fields. I mean, in reality, repr is called NS from. I don't know what N is, but S is from sum, and fields is called NP from product. But
Like n sums and n products.
yeah. Oh, right, and sums. So the generics SOP does this thing. I don't want to go into, because I want to sort of try to answer the things about the labels, but there is one thing missing here, which we would need to open more extensions. But one thing which is missing is here, we are calling equals. So this type is not really right. Because in order to be able to implement generic equality, we can only do that if every single type in our code implements equality. So let's do that. That's simple. So new thing, constraint kinds.
You know them by heart already before the compiler asks you.
Yeah, that's essentially what I do for a living, believe it or not. So so what we are going to do is to do this weird thing. So instead of having like a constraint, like an equality thing, we're gonna produce an equality based on the list. So we are gonna traverse the list, and then by traversing the list, we are generate the conjunction of all the constraints we need. And we can do that because in GHC, constraints like EQ are like other types. They just have a different kind, which is called constraint. So we will say all things in my list of lists are going to implement a constraint C, and I have a list of lists. So this is going to be a constraint, and this is going to be that's not a data actually. That's a type family. So if I have an empty list of constructors, there is no constraint to be done. If I have some constructors, then I will go and check with each of the fields, so C and X, and then I will keep checking constraint C, and this constraint is actually a parameter. So that's I don't know. This always looks to me very weird, but this is this should be a list of star, and now this is a list of a star, and generates a constraint, which I write wrong before, where and all one of C again. This is just no constraints. All one of C, that's just, please check C on the first element and then check C on the rest. So that's very weird, but essentially it's like, get the constraint C and go to levels deep and check on every single thing. So I think I'm going to get a compilation error because, yeah, constraint is not known, so don't worry. Import ghc.x. Yeah. Yeah, and now, what it tells me, not in a scope GQ prime.
Yep, same thing.
Oh, it's because
And 9.2 is not using GQ prime.
It's like the where clause is
Yeah, the where. Maybe I need to put it like this way. I'm not really sure.
I think it's when you pattern, like when you do the where clause, it's only attached to the very.
Oh, you're right. Yeah.
Oh, I see. Yeah.
No problem. Yeah. So now exactly it's telling us, okay, I'm sorry, but I could not deduce all these EQs because I don't know if you have EQs. So that's okay. We'll just say, okay, if all the things in my code implement EQ, then I can do this. And here I say if all my things in my constructor implement EQ, then I can do this. Hopefully it will compile. Yes! So by having like plain everything, I didn't invent that, by the way. So by playing all kinds of tricks of this, we got. I find this amazing because this is really like declarative on like if every EQ, then wow. So that's yeah. And you have metadata for this too. All one is checking like maybe it could be like all constructors and all. I'm just reusing the names from generic SOP.
Can you copy and paste the type family codes somewhere?
Yeah, it's in this library called generics-SOP. Oh.
We get this file.
I can send it to somebody and put it online. Yeah, I guess.
Put on Gitter or something. No, it's not Gitter.
Yeah, I will do that. I'll just put. Slayer is also a Slack channel. It's not a Gitter channel.
It's like there's both.
Oh my God. Okay.
You can just copy these files into the not copy.
Yeah, we'll just.
Upload this to Gist.
Yeah, well, I can do that. Okay, so that's. I can do the labels if you want, or we can just break and I can show to you instead. So feel free, of course. I mean, this is like. Feel free to. But if you have questions about this, just.
Yeah, there is a couple of, at least a few libraries around that. Uniplate, SOP.
Oh yeah, no. Uniplate. I mentioned at the beginning. So there is like two big ways to do generic programming in Haskell. You have like the type level thingy, which is like this thing. You represent things on the type level, and then you have the runtime level things, and that's uniplate, biplate, multiplate, and scrap your boilerplate. So everything which ends in plate, it's like other different approach, and it could be sometimes it's better because the other thing can handle like this is so tightly typed that I don't know. There are times where it cannot infer things, and the other thing it works at runtime, so it might be better in some occasions. I like this more.
What is the runtime representation of the co-product Haskell?
It's just a list. So it's a bunch of theirs,
Oh my god.
Oh, so
and then a here.
So it's very similar to the previous representation.
Yes, the representation it's almost the same.
So in Scala, we've been experimenting with an alternative co-product representation of this, which is just effectively an integer and the value.
Yeah, I mean, actually, if you ask me, you could even remove this with unsafe coerce if you don't care, because the type already tells you how many here and there you have. So you might even remove some of this. But yeah, that's.
Well, it's more so at runtime whenever you want to know which co-product you have in your hands, and you need. Well, I guess you're counting how many here's and there's there are.
Yeah.
If you just have the integer.
So we could do something slightly similar here. It wouldn't be so difficult. So we can have a type family which looks up a number into a string, into a list. So this is like. So if you are in position 0, then you have found whatever you're looking for. So I'm using here unary numbers. So otherwise, just keep looking. Yes, and I have to define my numbers. And then you could just say.
SOP does like that, right?
Now SOP does like the wrapper on top. I'm just trying to get what you did. It's not hard. So you have a lot of boilerplate here because you cannot actually pattern match on NAT on the type level, so you need to have something called a singleton, which is like a representation at runtime of this thing. So that's like defined somewhere. I'm just, or as like snat of n to snat of s of n, and then you could so this is like how you represent things. So you can at runtime remember which is this nat, and then you could have a different representation, representation 2, which just gets this thing, and then instead of doing this thing, says, you give me the number you want, represented at runtime and runtime as this singleton, and then you give me the fields on the nth constructor on my x's, and I'm happy to tell you that this is a representation for x's. Here you are.
Okay.
So,
Took someone 6 months to do that.
huh? That's great. You see, I'm really a very productive Scala programmer. I'm trying to tell every possible employer that's what I am. I'm not a Haskell weirdo. Good. So I think we can break here, and maybe we can look at the fields thing later after lunch, because I'm also like tired. I can with you. It couldn't be that hard. Good. Any more questions?
How hard it is the worrisome part.
Huh?
The fact that it's not that hard.
No, I mean it involves a bit of looking at documentation, because I never do metadata on these things. So I'm
Okay, you can just
yeah.
send me a link. I'll have a look.
Yeah.
I'll have a read.
So I'm in the business of producing generic programming libraries, let's say. Like my last 3 months have been about this. No, like in where I work at the university, the department does this thing from ages. So it's just I'm keeping doing this.
No, it's Miles Savius that is him in Scala.
Oh, Scala, yeah. Well, there's
No, this is, I mean, really, believe it or not, this is supposed to be like type trickery, which is well known. So doing this kind of things in which I define my type and promote it, and then I could not write an n here because an n is a nat, and again I need to turn my nat into a star so I can put it somewhere. That's always the same trick. You have something which is at type level, but you cannot have it at runtime. So you define a data type which just looks exactly the same, because you see that's exactly the same thing as before. That's a usual trick. That's called singletons. I think it's Connor McBride introduced this like maybe 15 years ago. So.
He did the structure boilerplate then?
No, that's Ralph Lammel and Peyton Jones, I think. Any more questions? Okay, then the question is, when do we have lunch? Which is now. Yeah, let's go.